Next, let us discuss the inductor formula. The voltage V across an inductor is directly proportional to the rate of change of current I flowing through it. It means voltage across an inductor. This is the electrical potential difference measured across the two ends of an inductor. This means that if one quantity increases, the other also increases in the same way. Rate of change of current di by dt. This refers to how quickly the current is changing with time, not the amount of current, but how fast it is increasing or decreasing. Mathematically, it is represented by V of t equals L times di of t by dt, where V of t represents voltage at time t measured in volts. This is the voltage across the inductor, which can change over time. L represents inductance measured in Henry. It's the inductor's ability to oppose changes in current. Di of t by dt represents the rate of change of current with respect to time measured in amperes per second. How fast the current is increasing or decreasing. The final explanation: the voltage across an inductor depends on how quickly the current is changing through it. Faster change in current means more voltage produced across the conductor. Next, let us discuss the inductor reactance. Inductor reactance refers to the way an inductor behaves in AC circuits. In simpler terms, reactance means the opposition an inductor or capacitor offers to alternating current. It's similar to resistance, but it only affects alternating current, not direct current. Inductor reactance means when AC flows through an inductor, the inductor opposes the current flow. This opposition is called inductive reactance. happens because the current is constantly changing and inductors naturally resist changes in current. The final explanation: inductive reactance is the resistance to alternating current caused by an inductor. It increases with frequency. The higher AC frequency, more the inductor resists current flow. Reactance is a characteristic measure of the opposition that an inductor gives to the changing flow of current. It means reactance is a type of resistance, but it's different from regular resistance. It only applies to alternating current where the current changes direction and magnitude continuously. An inductor opposes the flow of current when that current is changing. This opposition is not due to friction like resistance, but due to the inductor's magnetic field resisting changes in current. Inductors do not resist constant current like in direct current, but they do resist changing current like in alternating current. The faster the current changes, that is, the higher the frequency, the greater the opposition. The final explanation: reactance is the way an inductor resists changing current in an AC circuit. It increases with frequency and depends on how much inductor has the inductance. The reactance of an inductor is given by the following formula: X sub L equals 2 pi f L, or more clearly, inductive reactance equals 2 times pi times frequency times inductance. What each symbol means: XL represents inductive reactance. This is the opposition an inductor gives to alternating current measured in ohms. 2 pi represents a constant approximately 6.28, comes from the relationship between circular motion and frequency. F represents frequency of the alternating current signal measured in Hz. How many times the current changes direction in 1 second. L represents inductance measured in Henry. The property of the inductor that resists changes in current. Next, let's discuss how an inductor is constructed. Construction of an inductor consists of a coil that is formed by twisting wire into circles wrapped around a core and is used to store energy in a magnetic field while electricity runs through it. It means an inductor is made from a coil of wire. This is the main part of the inductor responsible for its function. The wire is wound into loops or turns like a spring. This shape increases the magnetic effect and helps store energy. The coil is often wound around a core made of air for air core inductors and iron, ferrite or other magnetic materials for iron core or ferrite core inductors. The core enhances the magnetic field, increasing inductance. When electric current flows through the coil, it creates a magnetic field. This magnetic field is how the inductor stores energy. The energy is only stored while current is flowing. When the current changes, the magnetic field also changes and the inductor may release the stored energy back into the circuit. The final explanation: an inductor is built by coiling wire around a core. This structure allows it to store energy as a magnetic field when current flows through the wire. The more loops and the better the core material, the more energy it can be stored. First, construct a coil of good conducting material. Usually, copper wire is used for this. First, construct a coil. This step is about building the main part of the inductor. A coil means winding the wire in a spiral or circular tape. The wire used must be a good conductor of electricity so that current can flow easily with minimal resistance. A good conductor allows efficient energy transfer. Copper is the most commonly used material for making inductors because it has very low electrical resistance. It is easily available. It is flexible and durable. In some high frequency applications, silver plated or enabled copper wire is used. The final explanation: to make an inductor, you start by winding a coil using a good conductor like copper wire because it allows electric current to flow efficiently and helps form a strong magnetic field. This core is then wrapped around a plastic or ferromagnetic material called a core. This means the wire already shaped into a coil is wound around something. That something is the called core. The core can be plastic or air, non-magnetic, used in air core conductors. Ferromagnetic material like iron or ferrite used in iron core or ferrite core inductors. Using magnetic materials as the core increases the inductance by concentrating the magnetic field. The object that the coil is wound around is called the core of the inductor. The final explanation: in an inductor, the coil of wire is wound around a central core, which may be made of plastic, air, or ferromagnetic materials like iron or ferrite. The core helps shape and strengthen the magnetic field, improving the inductor's performance. Number of twists of the wire raises the induction value, and the use of ferromagnetic material also ensures high permeability, which results in higher inductance values. It means number of twists of the wire raises the induction value. When you increases the number of turns in the coil, the magnetic field becomes stronger. More turns means more magnetic field lines, that is, greater inductance. So, inductance increases with the number of loops. The use of ferromagnetic material also ensures high permeability. Ferromagnetic materials like iron or ferrite are used as the core inside the coil. These materials have high magnetic permeability, meaning they allow magnetic field lines to pass through easily and densely. Combining more turns and high permeability core gives the inductor the ability to store more magnetic energy. The final explanation: more wire turns means stronger magnetic field, that is, higher inductance. Ferromagnetic core means better magnetic field concentration, that is, even higher inductance. These factors helps the inductor store more energy and resist current changes more effectively. The loose ends of the wire can be further connected to wires or devices, making it simpler for them to join with electronics. It means these are the two terminals or open ends of the coiled wire in an inductor. They are not connected to anything yet. These ends can be attached to other components in a circuit, such as resistors, capacitors, power supplies, microcontrollers, and printed circuit boards. This allows the inductor to be part of a working circuit. Attaching connectors or terminals to the loose ends makes it easy to plug the inductor into any electronic system. This improves modularity, ease of assembly, and maintenance in circuits. The final explanation: the two loose ends of an inductor's coil are meant to be connected to other circuit components. This makes it easy for the inductor to be integrated into various electronic devices and systems. Inductors are formed in various shapes and sizes depending upon the requirement of the device. It means inductors are made in different shapes and sizes based on what the electronic device needs. Small inductors are used in phones or tiny circuits. Large inductors are used in big machines or power systems. Each device needs a different types of inductors, so they are designed to match the need. Below is a simple diagrammatic explanation of the construction of a simple inductor. This means the diagram explains how a simple inductor is made. It shows the construction of the inductor in an easy to understand way. This is a diagrammatic explanation of the construction of a simple inductor, where core material, the long central part, is called the core. It can be made of air, iron, or any magnetic material. It helps to increase the magnetic field strength, where number of turns n. The wire is wound around the core in loops or coils. The total number of loops is called the number of turns. More turns means more inductance, where length L. The total length of the core or coil. Inductance depends on this length. Longer core means lower inductance, where cross-sectional area A. This is the thickness or area of the core when cut across. A larger area allows for a stronger magnetic field, where flow of current I. Current flows through the wire. This current creates a magnetic field around the coil, where voltage source. The inductor is connected to a voltage source. This source causes current to flow in the coil. The final explanation: an inductor is made by winding a wire around a core. When current flows, it creates a magnetic field. The inductance depends upon the number of turns, core length, cross-sectional area, and type of core material.